So in this video, we're going to talk about the geometry of vector addition along with the process of vector decomposition, which is a fancy way to say converting vectors from polar to rectangular form. And if that sounds a little bit complicated before I go to my slides, let's just kind of remember we said that vectors were nothing more than a tool to describe the physical world around us. So imagine I told you that I walked 10 feet north and then 5 feet east, and you were to kind of draw a vector diagram in order to describe that. Hopefully you would draw an arrow oriented in the north direction, and you would say that's 10 feet long, and then you would draw another. If I imagine this is my starting point, and I walked 10 feet north, and then from there I walked 5 feet east. Even if you didn't know a lot about vectors, you would probably draw a diagram that looks something like this. And then imagine that you wanted to show my net displacement or my resultant displacement. And remember, that's just a fancy word to say a vector that goes from where you started to where you ended. So if I started here and I went 10 feet north and then I went 5 feet east, the vector that spans from where I started to where I ended is just going to look like this, right? That's going to be what I would call my resultant vector. And in this case, it's a resultant displacement because each of these vectors is describing a displacement. And displacement is just a fancy word to say where you started to where you ended up. Now look at the geometry of what I've drawn here. Note that this closes a triangle of the two vectors I'm adding. So we're going to talk about two different rules for the geometry of vector addition in this video, the parallelogram rule and the triangle rule. And it's going to sound like they're these fancy rules that you have to remember, but really all they're doing is capturing the natural way that vector addition works. Since in this case, displacement is a vector, if you go 10 feet north and then you go 5 feet east, your resultant displacement, or the sum of your two individual displacements, is just going to lie along a triangle that basically closes up the two vectors when these vectors are arranged in what is known as a tip-to-tail fashion. So we'll get to all of that here in a minute. But just note that a lot of the words may sound new or they might sound complicated, but the concepts really aren't that tough. I saw the tail word and it messed up what I said. So when you take your physics class, or if you see vector addition in a math class, the way that it will probably be presented to you originally is that vectors add in a head-to-tail fashion according to the parallelogram rule. And remember that a parallelogram is nothing more than a four-sided shape where pairs of the sides are parallel to one another. So in this case, this is 1, 2, 3, 4-sided. And if you were to draw lines that extended along the sides that are marked by the vector A, those two would be parallel to each other, and same thing for B. So if I want to, what that is trying to say there is if you want to add A and B, two vectors, what you could do is you could take one vector and say it's A plus B. And you could take in this case, I'll go with my mouse, the tail of B and put it on the tip of A. So do that. And then draw a vector also, another copy of B, which is, of course, naturally will be parallel to the original B because it'll have the same direction. But rather than putting it on the tip of A, put it on the tail of A. So hopefully everyone sees that. You're trying to add A plus B, put a copy of B on the tip of A and one on the tail of A. And then in a similar fashion, once you have those two copies of B, redraw a copy of A at the end that goes to the tip. There we go. One goes to the tip and one goes to the tail. So hopefully everyone can kind of see the geometry there. It's one of these things, if I say too many words, it kind of overcomplicates it. But you'll create a parallelogram if you do that. And then by definition, the sum of those two vectors is going to be a vector that closes the diagonal of the parallelogram. So there is A plus B. What do I mean by is this consistent with physical intuition? Well, that's what I was kind of talking about on the dot cam before I got started. We know that this is naturally how vectors add. And hopefully you see as well when you look at this, that what this is really showing you is that vector addition is commutative, right? It doesn't necessarily matter, going back to my example on the dot cam, whether I walked 10 feet north first and then 5 feet east, or whether I walked 5 feet east and 10 feet north. I'm going to get to the same point either way. And that's because vector addition is commutative. And commutative mathematically means that you can just do it. You can swap the order on the operation. So if you look at that, so you can kind of see it here. Imagine that these are displacement vectors and I'm starting at this point. It doesn't matter if I do A first and then B, or if I do B first and then A, I add up in the same spot in each point. And if you think about what I'm asking you here by questions, if you, given the prior example of scaling by -1, how do you think vectors are subtracted? Well, what if you were to try to write, instead of A plus B, this shows you how to do that, A minus B. Well, remember that all multiplying B by a minus will do, it won't change its magnitude at all. it will just rotate its direction by 180 degrees. So that's how you actually subtract vectors. You don't have to learn anything new. You just take the vector that you're subtracting, you scale it by -1, which will rotate it by 180 degrees, and then you do your standard addition. And really the reason I'm not saying too much about that is no one adds vectors geometrically like this. You use the decomposition techniques that we're going to talk about later. So there's no point in really going over all of that detail for subtraction in a geometrical interpretation. So if you just focus on half either side of this parallelogram, either the left side or the right side, you see even the parallelogram rule is more complicated than it needs to be. These vector addition geometrically can more easily be interpreted using the triangle rule. I just wanted to show you the actual parallelogram rule because if you've seen it in a physics class or you've seen it in a math class, that's probably how it was presented to you. But engineers traditionally just deal with, vectors add according to the triangle rule. And when you want to add vectors according to the triangle rule geometrically, and we'll do an example of this in a dedicated video because you will have both a homework and an exam question on it. The way that you do it, if I want to add v to u, is I take v and I put its tail at the tip of u. So notice that v has the tail of v at the tip of u, and they call this tip-to-tail arrangement. As long as the vectors are arranged in a tip-to-tail fashion, then the resultant vector, and again, resultant is just a fancy way to say sum, the two that are being added together, is going to go from the actual tail of the first vector to the tip of the second. So hopefully that is just easier to look at geometrically. So let's talk a little bit about this concept of vector addition the concept of vector decomposition, which is going to be very useful for performing operations like addition and subtraction. And basically the key idea is this. You think about having if vectors are so common in our life as engineers, if every time we add them, we have to make drawings, that's going to take forever. It's not going to be an efficient approach. So we're interested in a way that we can make vector addition look more like scalar addition. And the way that we're going to do it is through this decomposition technique here. So when you think about vector decomposition, what it basically means is to write a vector as the sum of two other vectors, where those two other vectors are basically just weighted combinations of these very simple vectors. That was a lot of words. We'll talk about what it means here. But if you think about here, if you have the vector v that is in black, if you chose to say that I'm going to decompose it, and don't worry about how we actually did it now, into a vector that was purely horizontal and a vector that was purely vertical, naturally, this satisfies, if you look at this diagram here, this is the parallelogram rule. There's the original A, there's a copy of A, there's the original B, there's a copy of B. They form a parallelogram, and the sum vector just closes the actual diagonal here. So what we're doing here is we're trying intentionally to write V as a sum of two other vectors. So it's a little confusing because what we were talking about previously is if I give you two vectors and then you add them together. We're kind of going in reverse now. We're given a vector and we're trying to find how we can write it as the sum of two vectors. But we're particularly going to be interested in these type of problems of doing a specific type of decomposition, which is where we write them not as the sum of any two vectors, but the sum of two vectors that are arranged in this case, because we're only going to work in two-dimensional examples, the sum of two vectors that are aligned on the x-axis and the y-axis. And that relates to a concept and a word that you want to know as you go down your engineering math route, which is called a basis vector. And here's the basic idea that I give you for what a basis vector means without having to read the actual, the text there. I'm sure that many of you, maybe, who knows, like to cook. And when you think about people that are really, really good at cooking, what makes them so good is they have kind of a basic set of ingredients that they can combine in pieces and parts. They can take a little bit of this, they can take a little bit of that, and so on. And they can put it together and they can really make anything. And that's exactly what the idea of a basis vector is. If you have any vector in two dimensions, what we're going to see is that you can write it as a sum of so much of this what's called an x-hat vector and so much of this what is called a y-hat vector. And we'll actually go and look at that a little bit later. However, the key thing to know for now is the basis vector. It's kind of like your ingredients. It's if you have a set of basis vectors, they're all you need to make any other vector that you want to make. And those basis vectors, by definition, are going to have a magnitude of 1, and we're going to adjust the magnitude by the scaling that we talked about in the earlier lecture this week. And in addition, if you combine them together through scaling and you add them, you're going to be able to make any vector in the space, which is what I was just kind of talking about there. So how do you actually, what do the basis vectors look like? And then how do you actually do the decomposition? So here you can actually see a vector which has been beginning to be decomposed into horizontal and vertical components. And sorry for the resolution of this. When we do the example, I'll actually write one out step by step. And that's probably what I'm sure the majority of you will end up watching. But I just want to kind of get your head wrapped around the basic process of what you're going to try to do. So basically, if you have a vector, you're going to draw a new coordinate system, and you're going to, if the vector is not drawn in the coordinate system, because a lot of times in these problems, they just say, oh, a vector has this magnitude and it has this direction. So what you want to do is draw it and put its tail at the coordinate system, and then go to the tip and drop perpendicular lines, perpendicular in the sense that you're drawing just a line to the axes, and that line should make a 90-degree angle with the axes. So there's your perpendicular line to the x-axis. There's your perpendicular line to the y-axis. And what you then want to do is just kind of look at how you could write this vector as the sum of two vectors, one of which is purely along the x-axis and one of which is purely along the y-axis. And that's always going to be pretty easy to see geometrically. The question is just, what do the weights of those vectors need to be? And more particularly, if you're always writing it as a vector that's along the x-axis and along the y-axis, the basis vectors in that case are just going to be a unit vector that goes out along the x-axis and a unit vector that goes out along the y-axis. And unit vector just means that it's 1 unit long. So these basis vectors, you can either write them in physics, oftentimes they're written as I hat and j hat. Oftentimes in engineering, we choose to use x hat and y hat instead. And this is kind of what I'm showing you down here. Again, part of the confusing thing in engineering, because we borrow from so many different disciplines of engineering, physics and math, is that there's a lot of different notations. So sometimes you'll see these unit vectors that you're going to weight together and add in order to make a vector written as I and j, and they're just going to be bolded. So naturally, when you see I and j, you know that just to kind of go to my DocCam here so I can make a little bit more sense. The vector I, and since I can't write in bold, imagine that's in bold there. That's I. Another way to write it is I hat. Another way to write it is x hat. And in a similar fashion, you have this vector j, which that's my attempt at bolding. Don't laugh. And then it can be written as j hat, and it can be written as y hat. And what these basically mean are this first vector is nothing more than a vector that has unit length, meaning that it's 1 long, and it goes out along the positive x-axis. And this is 1. And the second is unit length, but it goes out along the positive y-axis. And the idea is if I can make these arbitrary length and I can use negative signs to flop their direction, I can take any vector in the plane, any vector I want to sketch, and I can write it as a sum of those two vectors in a weighted fashion. So that is the idea of your basis vector or your unit vectors. For those of you where I'm going, I think the reason that typically in engineering, x hat and y hat are preferred over I hat and j hat is if you're familiar with electrical engineering, which you will, if you're not, you're going to be in a few weeks. We deal a lot with the concept of electrical current, and electrical current is represented as a symbol in an equation using the actual variable I. So you usually try to avoid I. And since electrical engineers need complex numbers a lot as well, since I is already taken, they'll use j for the square root of -1. So it's kind of just convenient to us. So I know that was a lot of theory. What you want to do now, if you're confused, is don't panic. I'm going to do 2 separate videos where I do one kind of showing the triangle rule, geometrical interpretation of vector addition, and a second which shows the actual decomposition process. And that's what you're actually going to be doing on your homework. So as you do your homework and then translate onto your exam, just try to follow what I do in these 2 examples. And if you have any questions, feel free to reach out.